Welcome to a new episode of the ITU Journal webinar series, where you can find insights and forward-looking research on future and evolving technologies. The ITU Journal is an international journal providing complete coverage of all communications and networking paradigms, free of charge for both readers and authors. This publication considers yet-to-be-published papers addressing fundamental and applied research, building bridges between disciplines, connecting theory with application, and stimulating international dialogue. Its interdisciplinary approach reflects ITU's comprehensive field of interest and explores the convergence of ICT with other disciplines. We count on your support to make this webinar an interesting experience. Please submit your questions via the Q&A channel at the bottom of your screen. All questions from the audience will be taken during the Q&A session after the talk. The meeting is being recorded and the recording will be made available on the webinar website. Closed captioning is also available for this event. You can enable this by clicking on the closed caption icon at the bottom of your screen. We hope that you will enjoy the talk and we encourage you to stay connected until the end for the Wisdom Corner. I will now give the floor to our Master of Ceremonies.
Hello, and welcome to the webinar series with academics of the IT Journal on Future and Evolving Technologies. My name is Alessia Magliarditi from ITU, the International Telecommunication Union, the United Nations Specialized Agency for Information and Communication Technologies. It is my pleasure to open our 9th webinar of the season with Professor Ana Perez Neira. Please submit your question via the Q&A channel. We will address them to our speaker during the Q&A session. After the Q&A session, as just announced by our avatar, I will moderate the Wisdom Corner, live life lessons. So please stay online. Our speaker agreed to a personal chat. She will share with us some lessons learned over the years that might perhaps be useful for some of you. I'm pleased now to introduce Professor Iana Kilditz, Editor-in-Chief of the ITU Journal and founder and president of Truva from the United States. Professor Kilditz is Ken Byers Chair Professor in Telecommunications Emeritus at the Georgia Institute of Technology. Professor Kilditz has established many research centers worldwide, including in South Africa, Spain, Saudi Arabia, and Finland. He's Editor-in-Chief Emeritus of Impact Factor journals, highly cited and at the top of the most prestigious international rankings, visiting distinguished professor in several universities around the world. And his current research interests are in 6G wireless systems, terahertz communication, metaverse, and communication in challenged environments. So Professor Kilditz, the floor is yours for your opening remarks and to introduce our speaker and moderate the Q&A session. Thank you.
Thank you, Alessia. And I'm trying to see myself, but it's a little dark here. I hope you can see my face, but maybe it's not that important. So distinguished guests, esteemed colleagues, and honored participants, good morning, good afternoon, and good evening, wherever you are joining us from across our interconnected world. From magnificent city of Istanbul, a timeless bridge between civilizations and a symbol of unity between East and West, it is both an honor and privilege to welcome you to the Season 4, Episode 8 of the ITU Journal on Future and Evolving Technologies, in short form ITU JFAT webinar series. Today, we are exceptionally fortunate to host a visionary scholar whose pioneering work has reshaped the landscape of wireless communications, Professor Ana Perez Neira. Before we proceed, allow me to reflect on the transformative mission of the ITU JFAT Journal. Since its inception in December 2020, the journal has stood as a global beacon of open access innovation, forging an essential bridge between academia and industry while democratizing access to cutting-edge research. Each submission undergoes rigorous peer review, ensuring that only the most visionary and impactful contributions shape the future of the technology. The remarkable ascent of ITU JFAT as a premier publication owes much to an exceptional team: Suzo Ono-san, Bilal Jamusi, Alessia Magliarditi, Erika Campilongo, Maria Otero, and many, many others whose unwavering dedication has been instrumental in our success. To the brilliant minds in our global audience, we extend an open invitation for you to contribute your pioneering research and join us in propelling the next wave of technological advancement. I'm also delighted to announce that ITU journal FET has been officially indexed in the Directory of Open Access Journals, in short form DOAJ, a milestone achievement that amplifies our global reach and reaffirms our steadfast commitment to open knowledge dissemination. Now it is my distinct honor to introduce today's eminent speaker, a trailblazing researcher and extreme academic leader, a driving force in telecommunications, a dear friend, Professor Ana Perez Neira. Professor Perez Neira is a full professor at Polytechnic University of Catalonia, in short form Universitat Politécnica Catalunya, Signal Theory and Communications Department. From 2010 to 2014, she served as Vice Rector for Research at UPC, and today she leads the Director of the Centre Tecnologia de Telecomunicación de Catalunya, in short form CTTC, which is a well-known research center in Catalonia. A fellow of both IEEE and EuroCIP, she has been recognized with prestigious distinctions, including the ICREA Academic Award and Narcisse Montreal Medal, honoring her outstanding contributions to science. Her research spans multi-channel signal processing optimization and satellite communications. She has played a pivotal role as coordinator of the European Space Agency's satellite network of experts from 2015 until 2025, fostering a leading global community in this field. With an extraordinary academic legacy, she has authored over 80 journal papers, 400 conference papers, and 7 co-authored books, delivered 70+ invited talks, and led more than 30 research projects. Her innovative spirit is further advanced by 8 patents, and her leadership in chairing major international conferences, including ICAPS 2020, which made history of the first fully virtual IEEE conference, and uniting 15,000 attendees worldwide and the pandemic, amid the pandemic. An elected member of the Royal Academy of Science and Arts of Barcelona and the Royal Academy of Engineering of Spain, Ana embodies excellence, leadership, and relentless innovation. I first had the privilege of meeting Ana nearly 2 decades ago during my time as a visiting professor at UPC in Barcelona. Since then, our paths have been crossed many meaningful ways, most recently at the Huawei workshop in Sochi in 2019, just before the COVID, which messed up our lives, as you all know. Ana is not just an exceptional researcher, she's a true luminary in telecommunications, whose 2 decades of groundbreaking work have set the high standards in academia. Her relentless pursuit of excellence ensures that her contributions remain at the forefront of technological evolution. Dear Ana, today we are truly privileged to have you with us. Your insights will undoubtedly inspire new paradigms, challenge inventions, and ignite the minds of future innovators. Ladies and gentlemen, please join me in extending a warm and resounding welcome to Professor Ana Perez Neira. Ana, it's yours.
Thank you, Ian, for the invitation and for this very, very nice introduction. Let me share my screen. I hope you can see that. Yeah. So good day, everyone, and welcome to this talk. It's going to be on expressive neural networks, and the intent is to go beyond the black box artificial intelligence architectures. The work has been done together with my team at CTTC, Sara, Marc, Miguel Angel. And CTTC, as Ian has said, is a research center in Barcelona area. And now it has to
Is
go.
Miguel still around, Ana?
Yeah, a student. He says that it's like a student. He comes whenever he wants. Yes.
That's cute.
Yes.
He's a fan of Atletico Madrid. We used to have lunch and talk about it. Anyhow, tell him my regards. So please.
I will do. Thank you. I will do that. Yeah. So I'm trying to change to the next slide because now. Yeah, so the current neural networks have made remarkable progress, but there are still several key areas that need improvement. And this talk addresses two of these areas. One is the interpretability and explainability. So neural networks are largely black boxes, and there is a need of methods to visualize and understand the internal representations, tools to explain the decision-making in a human interpretable terms, and models that provide confidence, measure, and control of the design. And the other area that we are going to address is the scalability and efficiency. So state-of-the-art models are large, expensive, and energy intensive. And there is a need of efficient or light AI architectures that we are calling expressive neural networks. And also there is a need of sustainable AI via reduced training time and also reduced number of computations. My field is signal processing for communications. And in the future, communication networks, they are foreseen to enable edge computing. That means that the devices at the edge of the network, the cell phones, the tablets, sensors, cameras, are going to compute AI. The reason is that they are gathering so much data because of social networks or because of their sensor technology that if they have to deliver wirelessly this data to the core of the network, to the data center, so that they process it and they feedback their decision to the device, that would create large traffic on the network. So the solution is, or the vision is, that these devices are going to do locally the AI processing to extract some semantics, some features, and only send these features to the cloud, to internet, in order to avoid traffic bottlenecks and also in order to enable real-time applications, because they will be able to make decisions too, as they are doing this AI processing. Moreover, the future 6G networks will seamlessly integrate the satellite and the terrestrial communications, so the new 3GPP radio standard will make satellite just as another AI node at the edge of the network. And this is even more a more demanding node, because they have limited bandwidth and the time window is really short. If it's a low Earth orbit satellite, they move around 7.5 kilometers per second. So on the time window they have to connect to a specific gateway on the Earth is really short. Then they have limited onboard computational capacity, because the more capacity they have, it's more weight to launch the satellite. This is more cost, and this is to be avoided. And also because they are limited energy consumption. Their source of energy are solar panels. So all in all, in both the terrestrial and the satellite segments, these edge nodes can only afford low complexity, computations, and scarce energy resources. So with that, they must carry out task goal-oriented communications with AI in order to extract features and don't burden the whole network with a lot of data. Okay, so this motivates the talk on explainable and expressive AI, because this is desirable, at least in this setup. So my talk is going to first introduce the expressive neuron. We call it expressive neuron. It is a DCT-based neuron. DCT stands for Discrete Cosine Transform. Then I will explain why the DCT, because it has very nice properties for function approximation, for learning a nonlinear function, and I will illustrate that with a non-trivial example about blind source separation of nonlinear coupling. Then I will use this expressive neuron to build up an expressive neural network. I will explain why it is expressive, why it is more explainable than other solutions, and then I will compare it with state-of-the-art neural networks through 3 different applications, and then I will come to the conclusions. So the starting point is the perceptron, right? It was devised by Rosenblatt in the 60s, and he was trying to mimic a biological neuron. The input weights, the input signals, weighted by the synaptic weights. The core of the perceptron is combining them. And if this signal out of this combination goes up a threshold, then it triggers an electric signal that is communicated to the next neuron. So this activation function, this step function, was later substituted by a sigmoid, because the sigmoid has a continuous gradient, and then we can do gradient descent and nice learning for the synaptic weights and confer intelligence to the neuron, to the perceptron. And the activation function is really important, not only for the learning, but for the representation capabilities of the perceptron. It's the main difference, this activation function, with respect to any other linear filter, right? So what I'm going to explain here to introduce is make this activation function adaptive together with the synaptic weights. This is the first aspect, in order to confer more representativity capabilities to the perceptron. And then how can we adapt this function, this activation function? Well, we have to parameterize it, and we are going to use the discrete cosinus transform to model this nonlinearity. This is the innovation that we introduced, and this is the so-called expressive neuron. And I'm going now to explain about the DCT, because this neuron comes from the signal processing perspective completely. So why the DCT? If we have this sigma, which is a nonlinear function, the x domain needn't to be time, is any x, okay, any value. And if I want to represent this function, I can use the discrete Fourier transform. I compute it, I get some coefficients. As the axis is not time, the coefficients needn't to be frequency. It's just the Fourier transform domain. These coefficients allow me to reconstruct sigma, okay, with the, well, it should be the IDFT. This is the expression that you're familiar with. The thing is that this sigma hat is an approximation of the actual sigma. Why an approximation? Because the DFT is assuming that the signal repeats periodically. And in this repetition, there can be abrupt changes. And these abrupt changes cause that some of the Fourier coefficients have high magnitude, because there is an abrupt change, so it's like a high frequency, right? A high term that should be represented by the DFT coefficient. If we want to avoid these abrupt changes and maybe then make better or obtain better coefficients, we can do some transformations to the sigma, to the function. So we have this nonlinear function that we want to represent, but before doing that, we translate it, consider that has even symmetry, then we double the range, the input range. And then if we compute the discrete Fourier transform coefficients, we obtain that they are much less. The energy is concentrated in less number of coefficients, because the periodicity that it's assuming, the DFT, is now smooth. There are no so many abrupt changes, right? So with this manipulation of the signal, because I am representing the same function sigma, right? I have high energy compunction in the Fourier domain. The coefficients are ordered, that's important, higher to less. They come naturally with this order. There is low computational complexity because I double the range in the X domain, I half the domain in the Fourier domain, right? So I have half of the coefficients. And important, I can control the mean square error with respect to the number of unused coefficients. So if I only take Q1/2 coefficients, the error that I am incurring when representing the sigma is the one that you have here. This is the power error. So with this translation and symmetry that I have enforced to sigma, and I compute the DFT, this is the resulting expression. There is no exponential anymore. The even symmetry results in a real Fourier transform with Fk real coefficients. Well, to this expression, it has a proper name. It's the discrete cosinus transform. So it comes from the DFT doing these small changes to the initial signal to gain in this efficiency of concentrating the energy of the now Fourier coefficients or discrete cosine transform coefficients. In fact, the DCT is familiar to all of you. You use it for any YouTube, any Netflix, any video in Instagram, TikTok. They use this DCT because the DST is used in MPEG, in JPEG standardization to compress any video or images. And it is so efficient in energy compression that maybe with 1% of the whole image or the whole video, you can reconstruct it in your mobile, in your TV set, without noticing any degradation. So it's really a star application. And maybe because of this success, the other uses of DCT have been forgotten. And we retake them. And this is what we are going to do right now, to use it to represent the nonlinear activation function of a neuron. Okay? With the difference, or with the important aspect, that the coefficients of the DCT, we don't know them, we are going to learn them. And now other good properties for this learning appear for the DCT. And this is something that it's not very well known. We did this in this paper. We just explored them. They are easy, but it's something that people really didn't thought about that. So if I have X sigma pair, I can use a supervised learning to train and obtain the FK, the coefficients of the corresponding DCT representation. So I have just a linear filter that can be governed with the error of the output of the filter. The input is not X, but the cosinus of X. And the thing to be learned are these coefficients of the DCT. Okay? And using the mean square error, I can use a gradient descent to obtain these coefficients. And the nice thing that I want to stress is because of how the cosinus behave, there are very good properties of this of good convergence of this gradient descent algorithm. To guarantee the convergence for any gradient descent operating on an MSC, we know that the adaptation step, the mu, must be the inverse of the maximum eigenvalue of the correlation matrix of the input. So the inputs are the cosinus. The correlation matrix are orthogonal cosinus. So it's a diagonal matrix with all the elements in the diagonal equal to the power of the cosinus, 1/2. So the maximum eigenvalue is 1/2. So if I am substituting this, I get this red expression. So the mu, whenever I have to learn these coefficients, is 4 times alpha, which goes from 1 to 0, and the number of coefficients to be learned. So easy. With this expression, I guarantee convergence. How fast? Well, it depends on the alpha. And also because it's a gradient descent, we know that the time to converge depends on the final error that I can support. Okay? And the expression is this one. So if we isolate the number of iterations up to converge to have a final error epsilon n, it is inverse proportional to the minimum eigenvalue. The minimum eigenvalue of a diagonal matrix with all elements equal to 1/2. So the eigenvalue spread is 1. And this uniform eigenvalue distribution implies that the learning dynamics are identical across all coefficients directions, eliminating the use of slow convergence typically caused by eigenvalue disparity. There is no dispersion of eigenvalues. And because the matrix is diagonal, it provides also stable convergence to all the coefficients and fast. And that's really important. We control very much the learning. Okay? If we further work out this expression, because we are using an stochastic gradient, least mean squares, then we obtain this final expression, which depends on the minimum error in our approximation, which we can also control because it depends on the coefficients of the DST that we are not considering. Some examples. Imagine that we use the DCT to approximate this orange curve, which is a compounder. Compounder is used in acoustics. It amplifies, or in audio, the low values, amplitude values, okay? And we want to learn it. So we model it with a DCT, and we have to learn the coefficients that model this nonlinearity. The coefficients are these orange ones, and this is the learning curve on the left-hand side. We have the different lines are indicating the different values of the convergence, number of iterations to convergence, depending on the expression that we use. The measured one, which is this continuous line, is the one that we have seen before. It depends on the alpha. The alpha is set up here, and depends on the minimum error. We have only considered 12 coefficients, so we can compute that. If instead of a compounder, we use, I want to approximate a step function with the same number of coefficients, 12, we have this orange ringing line. So this is the learning curve. We have more error, but not because of the adaptive algorithm is not doing it properly. It's just because I am using the same mu, the same alpha as before, right? But now, because we have, we should have taken more coefficients to approximate this curve, which is more difficult, we have more final error, okay? So this is the measured number of iterations to converge. Now, this straight line is has increased the number of iterations because the final error is higher. I need more coefficients to adapt to make it lower. In any case, with all this introduction, I want just to show that the DCT has benefits in terms of function representation. So here you have on the right-hand side, in the blue, you have the number of coefficients that I need to represent this curve with the DCT. In this green one is with the discrete Fourier transform. So it's much better, the DCT, because of these manipulations of the signal. So I'm going to use that for the activation function. And then if I have to learn the coefficients to represent the activation function, I have shown that the convergence time can be estimated easily, can be controlled, and that the orthogonality of the basis functions of the cosinus provide a stable convergence of all the coefficients. So it's fast adaptation. Before getting into the neural network and the neuron, let me give you an example of, illustrate with an example, an application, how well the DCT approximates and can learn any nonlinear function. And the example will be how to separate in a blind way, without any reference, independent sources that have been mixed in a nonlinear coupling. So here we have A1 and A2. They are two sources, are independent, but they are coupled with these weights, A1, 2, A2, 1, and these F and G, which are nonlinearities. For instance, imagine, and the result is X1 and X2 are the observables, what I can measure. Imagine that X1 and X2 are the output of two antennas in an array, that they are close together and they are coupling. And this coupling can be nonlinear. And I would like to have these signals decoupled before transmitting. So to decouple from the observables, we are proposing the separation network. By the way, the details are in the publication that I showed in the slide before. So this is a feedback network that once I know I have estimated the nonlinearities that couple and the corresponding weights, I can subtract, and in 10 iterations, Y1 is one of the sources, Y2 is the other independent source. Okay? So we need to estimate the nonlinearities and the Cs. And we need to do that with, I'm going to use the DCT model for F and J, and I need to estimate the coefficients of each of the two models. I will use a gradient descent, right? And this is what I'm going to show you in the next slide. The next slide, there are a lot of equations. I just will comment some of the things because I don't want to get into the details of the blind separation, which is an interesting and difficult problem per se. I want you to show you the potential of the DCT in the function representation, right? But But just doing this gradient descent from the linear coefficients and from the coefficients of the f and the j, the gradient is here, the gradient of the output to the fourth value, to the fourth power. Why? Well, because we prove in the paper that this is a good cost in order to separate independent sources, right? The thing is the result. Look, here we have a nonlinear mixture of two single carriers. This is the compounder that is mixing, and the expander, the F and the J, that are mixing the two tones. These are the outputs, the observables, mix 1 and mix 2. And from them, without any help, just imposing that the fourth power should be minimized, I want to decouple them. And for that, I have to estimate these nonlinearities and the corresponding weights. So look, here I am superposing the green and the blue in both of them, which means that the DCT is able to approximate both nonlinearities. This is the learning curves for one and the other. And the result of the separation network is I have the two tones. Here's the periodogram where I can see them perfectly. And this is the mean square error from the separated signals. Okay, so it's performing really well. Instead of two carriers, I can mix nonlinearly a carrier and uniform noise. So these are the two mixed signals, the observables. I do the separation network. I compute the nonlinearities, the compounder, the expander, and the output is the tone and the noise. The noise is this uniform noise. This is the periodogram of the outputs. And this is the error of the separated sources. So it does well. If the mixture is linear, the DCT model learns the linear functions and the separation is perfect, much better than with the nonlinear mixture. So DCT per se is a very good option to estimate nonlinear functions in easy setups without having any neural network. Although I know there are works that are using neural networks for this blind source separation. It's something that we comment in the paper. Before getting to the neuron, let me further comment on the DCT and what happens if I want to do a representation not of one-dimensional signal, but of m-dimensional signal. So imagine that we have a two-dimensional signal, like an image. This is, for instance, 8x8 block image, okay, pixels. This is the two-dimensional discrete cosinus transform. The thing is, I don't like this expression so much as I like the one with one dimension. Why? Because now the number of parameters that we have to learn, the FK, to represent any image is grows exponentially with the dimensions, here with exponent to 2, okay? So this is something that I don't like so much. And the other thing is that if there are small changes in the function, in the 2D function to be represented, this translates into relevant changes in the discrete cosinus transform coefficients. So for instance, this is my original image, and C are the DCT coefficients. In orange are the amplitude values. Okay? If in the original image I change 3 pixels only, the corresponding DCT, which is the D, there are changes that I cannot control. They are not ordered as nice as it was ordered in the one-dimensional problem. So we are losing this scaling up or scaling down the coefficients if I want to prune the whole thing. So this was the motivation to say, well, why not use a one-dimensional DCT to learn the nonlinear activation function of a neuron and then use a neural network to represent any multivariate function. Okay? And that's what gives place to the expressive neural network. In the expressive neural network, we have this is one perceptron with the change that the activation function is learned, is adaptive, and it's modeled the parameters with the DCT. And this, so there are the inputs, the univariate nonlinearities that are modeled with DCT model for this neuron, for the other neurons in this hidden layer, and for the neuron in the output layer. This structure is shallow. It's only input, hidden, and output layer. And this is the nonlinearity with the DCT, and FK have to be learned together with the synaptic weights. And this is the expressive neural network. And in the talk, I'm going to show you the good performance with respect to other existing ones. It was published in the Journal of Selected Topics in SP last year. So one question maybe is, well, shallow. Yeah, so far I'm going to use a shallow structure because it's more interpretable and I will be able to control more than a deep neural network. Let's see if there are some, if its behavior at some point stops or I have to enlarge it. We will see that. But in principle, theoretically speaking, the Kolmogorov-Arnold existence theorem says that any function, any multivariate function can be approximated or can be represented by two layers, the Ross and the Fish. This existence theorem has motivated many neural networks, ours among others, right? No one says how to implement in a practical way the Ross and the Fish, but it motivates and it gives us breath to say, well, let's try with the shallow network with this ENN. Let's see what we achieve. What we call it, why we call it expressive? Well, it's expressive because of the DCT activation function. First, it's going to be adapted. Shouldn't be a sigmoid. It will be whatever the final optimization of the cost function says that it should be for every neuron. Every neuron can have a different activation function. Then it's easy to parameterize because as they concentrate so much the energy in the DCT representation, we have seen that with setting the number of coefficients fixed to 6, we have more than enough to represent any function. Even we can prune it. So it's not a parameter difficult to set. And very interesting, the DCT offers a periodic extension of a function representation. So here we have the blue is the sigmoid. If the input range goes from -1 to 1, our DCT is representing or approximating a sigmoid. But if the input range changes, then we have activation functions that differ without changing the DCT, okay? Just changing the input range. I will show you how this change in the neural network, okay? So this gives a lot of expressiveness to the same number of coefficients, the same coefficients in the DCT, okay? And that helps that a small or shallow expressive neural networks can capture high nonlinear relationships. This is an example. I will come to that later on. I call it, well, I call it Mickey Mouse. It's a classification map, binary classification map. And I make the ENN to learn this map, this classification. And the results that I am obtaining just with one hidden layer, shallow network, with only 6 neurons and 6 coefficients per neuron to approximate the activation function allows me to represent this classification map. I will show you later on, okay? Because this expressiveness of each of the neurons can do very difficult mappings. What about the explainability or the control of the ENN to understand it properly? Well, the bump, as you have seen, of this neuron is key. In general, the response, the bump is the response of the neuron with respect to the output space. The input range of the bump is determined by the synaptic weights, and the orientation is also determined by the synaptic weights. So imagine a perceptron with the ReLU. That's the a usual setup. The synaptic weights are the A's. So depending on the A's, this ReLU will have different orientations, and the input range where it is applied also depends on the synaptic weights. What we are incorporating is the bump, the shape of the bump, to give it more expressive, to make it more expressive through this nonlinear adaptive activation with the DCT. So the ENN, we can understand it in this shallow network as a weighted sum of bumps. We have the inputs, imagine it's two input neural network. And then these are 4 neurons in the hidden layer, and these are the input, output of the neuron mapping. See how the synaptic weights are included in this plot. So there are different orientations. Then we have the output layer, the rest of the neuron. And these omega weights are giving different relevance to each of these mappings. So at the end, we have this global response. And then also the NN learns the output nonlinearity. And this is a specific case where we learn this binary classification map that we have here, okay? Only with these 4 neurons. So the output activation in the ENN is also adapted. It will be a step function if the final goal is classification, or a line if it's regression. It will be learned automatically. We don't have to set it up beforehand. Okay? And of course, the more coefficients, the steeper will be the curve in the separation of 2 classes. So this step function with 20 or with 12 depends. But in any case, it's steeper than a sigmoid. How we initialize the ENN? The linear weights or the synaptic weights in the hidden layer, the A's, are initialized to provide bump diversity. So cover the whole 2P radiance with all the different orientations are covered. This is the case where we have 1, 2, 3, 4 neurons. So try to cover in this initialization all the possible directions. Then the expressive neuron, the DCT, are initialized with lines, the coefficients. And finally, the linear weights in the output layer are initialized uniformly to give the same relevance to all the bumps. So there is no secret. It's everything very mechanical, straightforward. About the training procedure. So by default, the expressive neural network is trained with mean square error because we are going to use it mainly for representation of function of any dimension, and with the stochastic gradient, with the least mean squares. And we will train the parameters with backpropagation, both those in the expressive neuron, the coefficients of the DCT, and those of the synaptic weights. And we will benefit from the properties that we have seen when adapting the coefficients of the expressive neuron of the DCT. The power is 1/2 because of the cosinus. It's really simple to normalize the gradient and to guarantee this convergence. For instance, we have here the gradient update of the output neuron of this that should be either a line or a step function. Okay, these are the coefficients of the corresponding DCT for that neuron, approximate that step function or line. This is the expression that I have shown you before. This is the same mu, the 4 alpha divided by the number of coefficients. And here we have, for instance, at the output layer, the W2 weights, they update also through the gradient, the rule chain, and again, it's very neat to formulate. So this approximation of the DCT is really fine. Okay, so from the learning perspective, using the DCT to model the activation functions brings the following benefits. The network size. The number of parameters in the network grows linear with the number of neurons, because each neuron only needs a small number of coefficients to model the activation, the corresponding activation function, and this Q, due to the energy compaction of the DCT. Backpropagation, so the tuning algorithm can be implemented because the DCT coefficients are real and they are ordered in decreasing magnitude. So if we see that at some point they are negligible, we can disregard the rest of them. That's really convenient and practical. And besides, I have shown that there are analytical closed-form solutions for the backpropagation training. The gradient behavior, so the basis functions, the cosines, are real and bounded, which prevents exploding gradients. And also, since the Fourier representation creates a periodic function, which doesn't saturate, it also prevents vanishing gradients. And finally, the task adaptability of the whole network, this last neuron. The output nonlinearity is automatically adapted depending on the task, classification or regression, without changing the loss function. Okay? One consequence of this explainability or control of the network is that it's easy to prune, easier than others. So imagine here that we have the goal is to represent, to do the classification with this, well, 4 white bar classification map, right? Binary map. And for that, this is the outcome that you have here on the right-hand side. And we have used a shallow network with a hidden layer of only 4 neurons. You see that 2 of these neurons, the first and the third one, are flat. So we can prune them. In fact, with one, also we already have the final representation. See an interesting thing, the final neuron, this step function, which is learned together with the others, it's upside down because we have to put the negative into the positive because the 4 bars are here below. That then it changes. So it changes the sign. So everything matches. And here we show how we start with 6 neurons and we get this accuracy of the classification. That's the number of correct classifying inputs in this 4-bar binary map. If with 5, this is the output, it's similar. With 4, so in fact, up to 2, as we saw it before, the results are very, very nice, very good, acceptable. So visually, we can prune it. Something that we cannot always do with other neural networks, right? For instance, with the same example, if we use, this is the ENN final outcome. If we use a multi-layer perceptron with the ReLU, it's not possible to get this periodicity. It fails. That is 72 only a percentage of accuracy. With the Kolmogorov-Arnold network, it fails. There is a lot of noise. With the Fourier, it also grasps this periodicity. This is just to show you a first snapshot. I will come to the details of this comparison in the next part of the talk. Okay? Because now, having explained how does it work, I want to compare it with existing networks. And for that, I'm going to show you 3 different applications. One is for 1-dimension function representation. The application 2 is for classification. And the application 3 is for 2-dimension function representation, or so-called implicit neural representation. So for the 1-dimension function representation, to show the capability of the ENN in front of others, I will consider prediction of chaotic sequences, okay, as a goal. So a chaotic map is a deterministic mathematical function that exhibits chaotic behavior because it's very sensitive to initial conditions. Let's see this example. So it's always the nth sample is completely determined by the previous sample, x in minus 1. This is, for instance, the logistic chaotic map. Here we have the expression. This logistic map is used, for instance, to model the growth population of the world. And xn is between 0 and 1, and the control parameter r is between 0 and 4. In this plot, it shows how, depending on the value of r, the chaotic behavior appears. Between 3.5 and 4, we see that any small variation on x0, the initial condition, can lead to very different output, fixed output values. So it's completely chaotic. On the other hand, below 3, the control parameter below 3 is deterministic. Okay, so we are going to set up R in this range to have a chaotic modeling and try to predict it with our ENN and compare it with other predictions from others, right? Which are the other neural networks that we are going to consider as benchmarks? The multi-layer perceptron with the ReLU, which is the most popular activation function. In this case, with the ReLU, there is no adaptive activation function in this case, right? With the Fourier, where we have sinus and cosines, sines and cosines, okay? Both adaptive also to model the nonlinearity and nonlinear adaptive function, and then the Kolmogorov-Arnold network, which models with splines, also in an adaptive way, the activation functions. In the comparison that I'm going to show you, to be fair, all models have one hidden layer and the same number of trainable parameters, which is around 60. And in the training set, 200,000 samples are considered, the LMS or the stochastic gradient for training, and to ensure a good propagation of the gradient, the learning rates in the output layer are smaller than in the hidden layer. Well, this is a piece of advice, a practical thing that we have observed. So let's go to the results of the logistic map. These maps are xn minus 1 in the x-axis, in the y-axis xn. Okay? With the ENN is perfect match. It's superposed. The ground truth, which is the dotted blue, with the red, the ENN. The ReLU tries, okay, more or less, and the CAN fails. That's with the same number of parameters. The Fourier does it pretty good. Later on, I will show in a table the numbers to see the fine detail of the error of these different approximations. Before that, let's go to another representation of another map, chaotic map, the Bernoulli chaotic map. The expression changes right now. We have a modulus operation, and this is the xn minus 1 versus the xn. Okay? Here we see that our network, the expressive, the ENN, with the DCT-based activation functions really struggles in representing the rapid variations of this sawtooth. Well, we have constrained it to have low number of coefficients. We are just doing this comparison. We have not further tried other kind of configurations with more coefficients. That's one of the things. We are interested here in the comparison with the others. In contrast, the ReLU here does it very well because it constructs the mapping with planar segments, so it's more suitable. The CAN and the Fourier doesn't perform that well. The thing is that if we compare the mean square error in the Bernoulli map, in this table we have the Bernoulli map and the other maps, but in the Bernoulli map, in fact, the error of all the networks, in spite of this visual appearance, are similar, 10 to minus 2, all of them, right? So the ENN is not performing that bad. For the logistic map, it was the best to perform, as we have visualized. And then we also tried with cosine map, cubic map. Only in the cubic map, it seems that the CAN did it better than our network, but it is also worth noticing that the ENN has less hyperparameters and a simpler configuration than the Kolmogorov-Arnold network, okay? And it's easy to interpret, okay? So there are these kind of trade-offs. This is for one-dimension function representation. Okay, we see the goodness of our network. Let's go to classification. And in this classification, we are going to do the following comparison. First, to compare the ENN again with a multi-layer perceptron, MLP with ReLU, fixed. Then with a sigmoid, MLP with sigmoid, fixed in this case, in this first comparison. Note that the output of the sigmoid saturates for an input of large magnitude, which is something that's why the ReLU was devised. And then we will compare it also with MLP, where the activation functions are approximated with a DCT, but with fixed coefficients trying to implement a sigmoid. The only difference with the sigmoid is that as it is modeled with the DCT, the function is periodic and doesn't saturate. In the comparison, all models have one hidden layer and the same number of neurons, 6. And in this first comparison, the ENN is the only one that adapts the neuron. Okay. Well, these are again the training set and the test set. Okay, I'll go to the solution, to the examples. In the classification table, here we have 8 different binary maps of different order: 1, quadratic, cubic, more than cubic, more and more difficult. And here we have the ReLU, the sigmoid, the periodic sigmoid, and the expressive neural network. In the first one, the ReLU, this is fit, this separation map, this classification for it. This percentage is the number of correct classifications and the probability of the accuracy or correct classification. But as we increase the difficulty of our classification map, binary classification map, we see that the ENN behaves very similarly, keeps up without increasing the number of neurons, without increasing the number of coefficients to model. The others begin to crash. Okay. Of course, and here you can, for instance, visualize in the last one, the Mickey Mouse appears again, which is the final map that is learned by the ReLU. Nothing to do with the Mickey Mouse, the sigmoid, or the fixed periodic sigmoid and the ENN. Of course, you can say, well, here we have that the ENN is adaptive, not only the synaptic weights, but also the activation function. If we did that in order to also to put, to stress the interest of adaptive activation functions in general, right? If we then do a more fair comparison and compare our ENN with other networks that adapt the activation functions, all of them around 70 trainable parameters, so the complexity is the same. Well, the ReLU is as before, doesn't adapt, no? But then we have the Kolmogorov-Alnov that adapt the activation functions with splines, and the Fourier with sines and cosines. We see that the Kahn and the Fourier, they see that there is something more than a donut, but they fail, and this is the accuracy. Okay. So how can we understand our ENN? Imagine that we want to classify with this donut map, binary again, and we use one hidden layer with 2 neurons. Neuron 1. In the first row, we have the input, output of the neuron, and the red and the green lines are the input range. It depends on the synaptic learned weights, okay? And this is the output neuron. The row below is the input of the network, the output of the neuron. So it includes the synaptic weights, and it's this 3-dimensional. And we see the different orientations due to the synaptic weights. They are combined, and with 2 different directions, at most what we can do is to square somehow this ring. However, if we increase the number of neurons to 4, more directions and curves appear in each of these neurons, and we finally can get this almost donut. with 6 neurons, we get it. If instead we use, and if there were at some point a flat neuron, we could prune it. Something that if we do the same exercise, but with a ReLU, it's not so easy to interpret. Here we have the same binary map to be learned in order to classify with a ReLU, multi-layer perceptron, one hidden layer, but with 12 neurons, 12 different ReLUs, and we just learn the synaptic weights, their orientations. Okay? This is the output. Of course, the ReLU cannot make it. Okay? But not only that, there are some of the neurons that are completely flat. This third one, or for instance, the 9th neuron. We could say, well, we can disregard and prune them. It's not like that, because the ReLU, this means that we are working in the negative part of the ReLU. They are stuck, so the whole MLP, it's stuck in these local minima. It doesn't mean that that the network doesn't need these neurons. It doesn't, that it's not taking advantage of them. Something that it doesn't happen with expressive neural network. Okay? And finally, for the classification, a multi-classification. And for that, we use the CFAR as the testing data, airplane, different set of images for airplane, mobile, bird, so forth. And now we are going to use an ENN to classify them. And we are going to compare it with an MLP. Okay? In this case, these are the results, the accuracy. Our ENN is better than the MLP. However, this is only just a promising or a result that shows the potential of the ENN. Although this is work that we are doing on progress right now, is the MLP, the multi-layer perceptron, is not the best one for image classification. It's better to use a convolutional neural network. And we are studying how to incorporate our expressive neuron in this different architecture. But even in this sort of brute force classification, is doing better than the MLP for the same number of parameters to be trained. And there is a last application and benchmarking, okay, with some nice and interesting results. At least I think they are like that. And it's implicit neural representation. It's two-dimension function representation, in fact. What it is the INR? So instead of representing a signal as a discrete data, INR models it as a continuous function using the neural network. The network encodes the entire signal implicitly. It learns the function that generates the image in this case. So it decouples the representation from the input resolution, from the pixels. It can sample at arbitrary resolution. To train the network, the input are the coordinates of the pixel, and the output is the value of this pixel. Okay, so that's INR. And the experiment consists in testing several models on the several neural networks on the implicit neural representation of different images. Let's take first the cameraman. And this cameraman, we have used it to train different networks with 300 epochs. Now we have a deep network in all cases for layers. The number of parameters to train up to 200,000, and with the Adam optimizer. And we compare the ReLU, the Fourier model, the CAN, and the Siren. We have incorporated, this is a new neural network because it's a strong baseline in INR tasks. And it has a non-adaptive function that is the sinus with W0 a hyperparameter. Okay? And it results very good in this implicit neural representation. So let's compare it with it too. This is the MSC of this representation with the different benchmarks. And ours is this, the ENN is the one with dark blue. It's much better than the others. In fact, the MLP or the Fourier, even the Khan, at 200 epochs, they don't seem to improve. If we want to visualize this MSE in the results, here we have, for instance, the ReLU suffers from the low frequency bias, struggles to represent high frequencies. And here on the left-hand side down, we have the ENN, which addresses the problem. It's similar to the siren. If we could amplify that, we would see that it's better, the ENN. Well, the MSE is better than the siren. We see it's 1 order of magnitude better. Let's go further. We have learned with this image representation that it's very important to learn the high and the low frequencies. An image is rich in low and high frequencies, right? And we must cover them accordingly. So we use, if we visualize the ENN that whose results I have shown you before, and take from the first layer the input-output of 2 neurons, neurons that have converged, the same for the second, the third, and the fourth layer. We realize that there are some neurons that grasp the high frequency, the neuron A and the neuron G, for instance. Whether there are others, like the H or the C, that grasp the low frequency content. And that make us to think, why not to try to integrate the low and high frequencies from the start, help the neurons to tell them, you are going to learn frequencies, right? Not a whole function approximation. So let's see what we did. In our ENN, we restricted the activation function with the DCT representation to have only 1 coefficient. They only had to learn 1 coefficient. So the activation function will have this expression. And the Q is the frequency, which is going to be between 1 and R. In practice, between 1 and 9, it was enough for the images that I'm going to show you. So there are no more to learn in the DCT, in the neuron. Each neuron handles a distinct frequency range. So it specializes on a frequency. And there are then less trainable parameters, because then the DCT coefficient is absorbed into the linear wave of the synapses. Then we also are proposing some novel way to initialize the weights. Okay, so they are going to be uniform distributed, minus T, and T should be that such the variance of the output of each of the layers is 1, and this can be computed as it is shown here. But let's go to the experiment. Now we are going to use neural networks of 3 layers only. Okay, less number of parameters as before, and we are going to use our ENN with 1 coefficient, 1 for each neuron, for each DCT. This is the mean squared error that we get, the blue one. It's really very good behavior in front of the other 2 for the same number of parameters. If we want to visualize that, we have done different tests with DALI picture, or with the image 2 of this lady, and then this snapshot of a video, image 3. For the DALI, here in the left down corner, we have the ENN with this randomized 1 coefficient DCT. Okay, see that it's similar, maybe the serine. If you amplify that, the texture of the skin, the details of the skin, you can see them better than in the siren. So it really performs well. For the lady, this picture has many sharp transitions in the pattern, clothing of the subject, and the texture of the background, in the furniture. So it's a complex picture. And we see that the ENN, the ENN that we are devising, performs much better. So the texture, for instance, of the furniture. This is the original image on the right-hand side, much better than the others. And finally, if this frame, which is just a snapshot of a movie, where there are we took it to have a model on different data statistics. Again, the ENN on the down left corner in front of the true image of the siren. It's maybe visually, maybe we cannot see some of the differences, but you have seen the MSE is really much less. And here you have. So in all cases, it's much less than the others for the same number of computations. It's very impressive. And well, and you can use these INR applications for super resolution. Although you train your image with an n by n image resolution, you can then be able to reconstruct the image with S by S, with S being higher than n, or image in painting. Although you train an image with missing pixels, you can restore these pixels. So this is the ENN reconstructing an image of this resolution, but it has been trained with an n by n resolution, not with 2 plus. We compare it with a double resolution, it's very similar. And if we train it with some erased pixels, the ENN can reconstruct it perfectly. And with that, my talk comes to an end. So I have just showed that DCT can provide a strong theoretical framework for function representation based on the signal processing principles, with a very nice learning of its coefficients. So it's very useful to represent the activation function in an adaptive way for a neuron. We call it expressive neuron. Then we use this expressive neuron in a multi-layer perceptron architecture to obtain the ENN, which is expressive, means that same performance with less number of parameters. It's more affordable, and explainable, which is easier to control and tune the parameters. And now the ongoing work is to use this expressive neuron in other architectures, as I have commented before. So that's all on my side. And
thanks a lot, Anna. It was very informative and excellent presentation. Thank you. And there is one question, but before I ask that one, I hope that there will be some more questions put in the Q&A box. In the meantime, I can start the questions, and I hope that more questions will show up. So the first question will be on the efficiency and scalability. And as you mentioned that ENNs may reduce the model size, do they sacrifice any generalization capabilities compared to traditional deep networks? How do they perform on out-of-distribution or adversarial examples, for example?
We haven't tested for in adversarial scenarios. The sacrifice, the first question, if we sacrifice everything in the generalization, well, in the last examples were a deep architecture. It was more than one layer, right? Because it was what the application, right? So, but in any case, when compared with other networks with the same number of layers, the number of parameters were less in any case because of this expressivity of the DCT, right?
Yeah, yeah.
So we are not losing,
okay.
In fact.
So then I have also another question about, given that large language models rely heavily on scale, could ENNs be integrated into hybrid architectures? For example, using ENNs for feature extraction and LLMs for reasoning? Yeah. Or are they fundamentally competing paradigms?
No, they are not competing. So we just studied in depth with the multi-layer perceptron architecture, but we want now to explore other architectures, and they are not competing at all. So we think this is another conception of the neuron, and let's see how far it goes to put it into a transformer architecture or a CNN or a recurrent neural network. So that's what we are now starting to do. Yeah.
Okay, good. So then another question is about the signal processing and AI synergy. That is, classical signal processing emphasizes sparsity and energy compaction. Does ENN inherently promote sparsity in activations? And if so, could this enable new compression techniques?
Yeah, that could do. So the pruning that I have commented is that visually it's easier. So when a neuron is not active, it's really flat. If the neuron is with the DCT model is stuck in a local minimum, it's not flat. It's has a slope. So we can really visualize and see when we can prune it. So in that sense, it can compact the computation. But furthermore, what we want to do but now this is going to be done when we put it into a convolutional neural network structure, how the DCT compression can help in the compression of the image and extracting of the features. And well, our intuition says that we are in the good track, but well, we have to work it out. This the intuition, yeah.
And also related to that, you mentioned this about ReLU-based networks, but here's the question that since DCT, discrete cosine transform, is widely used in image and video compression, like JPEG, right? And could ENNs naturally excel in multimedia tasks compared to ReLU-based networks? You put some comparisons, but what do you want to add to this?
I don't see if I understand the question. So
it's like the DCT is widely used in image and video compression, right? And if you have multimedia tasks, right, all of this image and video, integrated cases, and then the ReLU case. So is it better, or in other words, will it have better applications in this type of environments? That's the question.
It's a very high level question. So I would go back to the last answer. So intuitively, we may have compression benefits somehow within the neural network if we use the DCT. And that can then extrapolate to coping with multimedia. But we don't still know how, well, I cannot answer you further because,
Yeah, that's fine. So I just want to know about this. And another question is about overall for future cases. What are the current limitations of ENNs? Are there tasks, for example, autoregressive generation, where larger models still outperform them?
Well, yeah, but they are not competing, right? This is just a very starting point of a very limited architecture. Large language models, they use other kind of architectures, but the thing is go to the neuron and change that neuron in that architecture and see what happens.
Right.
So we foresee the spirit is try to reduce the number of computations, easy the training, and control what is happening somehow, at least visually. But that's it's not competing at all with LLM. We are just at the starting of the whole path.
And also a related question is about, can these ENNs inspire new training paradigms? For example, maybe I missed that in your presentation, replacing backpropagation with iterative signal reconstruction methods. Like backpropagation, you did not mention anything, or did I miss it?
Yeah. So we use backpropagation to learn also the coefficients of the DCT model.
All right.
And we take advantage of the good properties of because the DCT, the kernels are cosinus. They are ortho, they have power 1/2, and this helps to learn in a fast way at least these coefficients. So, but we are learning them with the backpropagation, the whole setup. Okay, so if we can use other learnings, but why? Or we should. It's another topic.
Of course, that's just I'm throwing in some questions.
Yes, please. That's nice.
You should, So actually, there is only one question still by Hesham Al-Bakuri. I hope he's still around. So he says, he's asking, have you looked at neuromorphic computing and its applications in the edge?
Yes, I like a lot the idea of neuromorphic computing. In fact, I try to merge it with the ENN. The thing with neuromorphic is it's difficult to to formally, it's more for the analog and circuit representation, but to do signal processing on them is very incipient. But I'm looking at that because for instance, in the DCT, there are cosinus. So it's a sort of frequency modulation that we are using somehow, or frequency encoding. And the neuromorphic, they are doing PPM, pulse position modulation. So try to mimic things and try to what I can learn from the neuromorphic model and put it into the ENN. So the answer is yes, I have looked it up, but so far there are different ways. And of course, in terms of energy consumption, the analog neuromorphic is much more efficient. But we cannot control it. And also the sensors should be also, the input should be from neuromorphic sensors. So it's another field, interesting also. This is another way to focus the whole thing.
Okay, so I'm still waiting for some questions, but unfortunately, no other questions are coming. So I'm also thinking to ask one more question at least, or is it one here? Still one question, right? And anyhow, so if we look at this INRs, I have also many questions about, and just a simple question for you. How do they differ from explicit representations, the implicit neural representations?
What is explicit representation?
Like images, 3D shapes, etc., right?
I don't
like INRs use neural networks, as you say here, to represent data like images, 3D shapes as continuous functions.
It's the same.
And explicit representations store discrete samples like pixels and meshes, right?
It's the same. So the same. We are interpolating somehow,
right.
Learning the object or the image in order to interpolate for the mixing pixels. So it's the same.
Right.
Yeah,
okay.
It's the same. It's the same.
And one more question I can ask you. Again, so here's again a general question.
Yes.
What are, you worked with INRS cases, right? What are the challenges of training INRS?
The challenges.
Like spectral bias, neural nets prefer low frequencies.
Yeah.
So convergence and balance of detail versus smoothness. You're right.
Yeah. So that's So there is a bias. We saw that in the different layers of the network, the high frequency, the more layers, the more high frequency could be able to be represented, right? And from that, where we thought, okay, why don't we simplify our ENN so that each DCT just has one coefficient and focus on one frequency, so that with the neurons we have more rich a spectrum of frequencies to be learned. And that's what we did with the random ENN, just to focus on different frequencies, each neuron and each layer. Yeah, because that's important, very important in INR. In fact, the siren, which is the other neural network that is very successful, is trying to do that, although the frequency is not learned. It's a hyperparameter that you have to set up from the beginning, and we learn it.
Thank you, Anna. It's very nice. I enjoyed the Q&A session also, and as well as your presentation. And I wish there will be more questions from the audience, but at least we have one from our friend Hisham. So Alessia is already here. So Alessia will take over for life lessons. And maybe we should remind the audience that these questions were not given to Anna before. So that's all spontaneous questions. And I hope you will enjoy her life lessons. So Alessia, please go ahead. It's yours.
Thank you so much, Ian, and thank you, Professor Anna, for your excellent presentation. So we now move to our Wisdom Corner, live life lessons, which aims at offering a unique and special angle to this series of webinars, so adding a personal touch. So I would start with my first question. Looking back on your journey, what is the most valuable life lessons or even failure that you have encountered that shaped your path, and how can this lesson inspire or guide those attending the webinar?
I would say you must like what you do. It's the only way. It's the only way to recover when you are doing something wrong and you get up again, and you must work a lot. So there is no other mystery but work a lot, and the only thing to work a lot is to enjoy your work. That's the summary. So simple, and then you don't pay so much attention to comments of others. You just work on what you want, and that's the thing. That's the main thing. I think that otherwise you cannot spend so many time.
Can you share? Do you remember any failure that you believe you had in your career, and an example if it comes to your mind?
I try to erase them. Yeah. Failure. Well, maybe failure, or sometimes
some hard lesson.
Well, a hard lesson. Maybe sometimes you ask yourself to put a very high level, okay, and when you don't get it, you get angry. Sometimes I have been my first enemy, in the sense that bad times have been created by myself more than by the others, right? And I have learned that this should be forbidden. This should not be like that. So I have learned from myself that bad times, so you have to treat yourself well. Although you must be ask yourself a lot, you must be happy with yourself. Yeah. So the bad times, I have created them myself. Yes, many times.
Yeah, thank you. In your opinion, which areas of study and telecommunications field hold the most potential for future researchers? Are there any emerging trends or groundbreaking topics that excite you and you would recommend students to explore?
Yeah, it's telecom, it's my field. I commented it at the beginning of the presentation. All these edge computing, so AI on very simple devices and wirelessly, because they will have to share computation. I have not talked about that, but well, how to share. The wireless media can help to compute. So there is a new physical layer there. Other thing is that the standards go that way, but in terms of research, there's a new area there. And then, looking at the space, I am always thinking that the space computer is coming somehow. So I think that overall now there are a lot of trends, new trends in telecom, but this over-the-air computing and edge computing and the satellite part, the satellite computing, I think there's a lot of things to be done there. Yeah, I encourage people to go there.
To go there, to study that. What key advice would you give to young professionals aspiring to build a career in academia or research? In your experience, what essential skills or qualities contribute the most to succeed in these fields?
You must like studying. Yeah, that's important. Studying
For sure.
And like to meet peers, because conferences, traveling is an important part of the academic life. Yeah, more than you realize. When you don't have it, you realize that it's part of the whole exchange of ideas and a whole fun. So these two things, I would say.
Excellent. And what first inspired your passion for your field? Do you remember how did you turn this interest into a meaningful career?
Well, it was by chance. So yeah, I was, yeah.
Most of speakers say that.
Yeah, but it's true. The telecom school was close to my home. And then
Aha.
I knew that I wanted to study something related to maths or physics.
Okay.
Okay, I know that.
Yeah.
And then, yeah, I saw that, why not? And I must admit that at the beginning, that was in the mid 80s. My background was nothing about computer. I have not programmed at all. I have not touched any circuit. That was not this technology training before. And I must confess that the first year was really tough. I thought, what I am doing here? I don't know how to, yeah. So that's why it's important to like study and to be curious and say, well,
Absolutely.
that's
Be curious. Very important. Thank
that's
you.
it. Yeah,
No, please.
Your vocation is something that you can build. This is something I would like to say. There are exceptional people that they are born with they know what they want to be in life, but the most majority don't, and it's something that you build along your life. Once you know more and more and more, your sensitivity grow and grow and grow, and that builds up your vocation, and then you are fun with that topic.
Fully agree. That's so true. Yeah. And my last question, among your career achievements, is there one particular contribution, whether professional, personal, that has a profound impact on you or on others? And what makes this accomplishment particularly meaningful to you?
In terms of professional career, when I got the tenure, I think that was, well, it was another stage. Then things change. I think that everyone should get the tenure because your life changes. And in terms of academic achievement, research, when I began to get familiar with the satellite segment and began to work with European Space Agency projects, then I like that very much, this niche. And then I got some first big project, and then I got a good result, and then I built on that. That's the thing.
Great. Thank you so much. Thank you very much for sharing your experience and providing some advice. Ian, for our closing.
Thank you, Alessia, and thanks a lot, Anna. I hope to see you again when I come back to Barcelona.
Yes, tell me.
Yes, I will, yeah. And so again, enjoy the evening, ladies. And also we thank the audience for listening to us and hope to see you next week. We have Osvaldo, right? Osvaldo Simone.
Yes, correct.
And so that will be another exciting webinar. So we have 2 more to go. And another one is Navid Nikain from ENNs. So then the season will be over. So thank you again, and enjoy the evening. Ciao.
Thank you so much.
Thank you,
everybody.
Thank you,
Thank you, Anna. Thanks a lot. Bye-bye.
Bye.